Section is about positive inotropes. So we just finished talking about a couple of negative inotropes. Remember, inotropes have to do with the force of contraction of the heart. And so we talked about two negative ones, which were a couple of antiarrhythmic drugs, and those were beta blockers and calcium channel blockers. Both of those are negative inotropes. This group of drugs are positive inotropes. And the whole idea behind them is when we have a weak heart that is not pumping blood very effectively, if we can make it more efficient in the way that it pumps the blood, then we're going to help that heart. So it increases the force of contraction, increases the heart rate a little bit, but the main thing is the force of contraction and helps to get blood around to the body. So three main categories. We're going to talk about the natural positive inotropes that we have in our bodies and animals have in their bodies. Catecholamines. Catecholamines are epinephrine and norepinephrine, and they are released by stimulation of the sympathetic nervous system. So again, the fight or flight system where all of a sudden we need to get up and go, run away, or stand and fight. So we have them naturally, but we also have synthetically synthesized ones. We're going to talk about pemobendin that actually has two actions, one of which is a positive inotrope, and digoxin. And digoxin is a drug. We don't use it as much as we used to, and you'll see why because of its side effects. But it has been used as both an antiarrhythmic drug. So I'm going to talk about that. So in some ways it could have been put in the last section, but it's more commonly associated with being a positive inotrope. That's why I'm keeping it in this section. So remember at the back of your chapter, there is a box that categorizes all the drugs. And I think it will really help you if you look at that and kind of think of these drugs in those terms. I'll have some review materials for you before the next exam, but you want to categorize these drugs somewhat on your own and make sure you know which they fall into. So digoxin is derived from this plant. This plant is the foxglove plant, really pretty flowers on it. But it was used in the past as a poison because of digitalis, which is in it, which is where we derive digoxin from. So we use a poison, but in this case, it's at a low dose, but it does have some side effects to it. And so it is used as a heart medication. So how do positive inotropes act? They basically act with calcium. So kind of the opposite of the calcium channel blocker, we're going to make this calcium more available or increase the affinity of it and the proteins that are in the little myofibrils. If you remember these little, the myosin and the actin, and calcium is part of this in making that contraction work. So they are going to increase that strength of contraction on a very, small level, on the cellular level, and increase that heart contraction overall. So these are the natural catecholamines, positive inotropes that we have in our bodies: norepinephrine, epinephrine, and dobutamine. And I've got this little animation. You do not have to memorize it, but it is kind of interesting. It's showing different how these are derived in our bodies. So norepinephrine and then epinephrine. And that all you need to know is that these two are our main neurotransmitters of the sympathetic nervous system. Dobutamine is a drug that you're going to see in your anesthesia class because we use it to help support a heart that is not putting out enough blood, and we get low blood pressure. It's one of the ways that we treat low blood pressure. So catecholamines are also called adrenergic drugs. They originate from the adrenal gland, and they are also called sympathomimetics because they mimic the sympathetic nervous system. We could also throw in a third name to them, and that is parasympatholytic. So we're going to counteract the parasympathetic nervous system with these drugs. So we can synthesize them. The main ones that you would see in practice would be epinephrine as an emergency drug to revitalize an animal that's in heart failure, and then dobutamine, which is typically used in a constant rate infusion, put in fluids in an animal that is under anesthesia to help get their heart, their blood pressure up. So they stimulate these beta 1 receptors. Remember, beta 1 receptors are responsible for the heart contraction strength and beat, and get it going again. We don't use these drugs on a long-term effect. Whoops, I'm going to go back up. Because of something called downregulation. Hopefully that sounds a little familiar. In the last section, when we talked about antiarrhythmic drugs, we were talking about upregulation. That had to do with beta blockers. Beta blockers blocked these very same receptors. And so what can happen when they get blocked is they put out more receptors on their surface. When they are overly stimulated, they start to pull in the receptors. These cells have a little bit of kind of recognition of where they want to be. They don't want to be stimulated too much and they don't want to be stimulated too little. So they have some control over those receptors. So in this case, with catecholamines that are stimulating those beta 1 receptors, they start to pull them in. And that is called downregulation. When we don't have as many receptors, we would have to add more of these to an animal system to get them stimulated. And we don't want to do that. So they're only used short term. We don't use them for long-term regulation of an animal that has congestive heart failure, that is, the heart is not working so well. All right, so this is the drug that we will reach for most of the time, and it's called pemobendin. There's a bunch of trade names. CardioSure is one of them. I have the other ones at the beginning of this section. And technically, this drug is an inodilator. So it has two effects: a positive inotropic effect, getting the heart to contract more effectively, but it's also a peripheral vasodilator. And we're going to talk about vasodilator drugs in the next section. But I'm going to give you the Reader's Digest version here, is that it's kind of like thinking of your vasculature as a large straw or a small straw. When we dilate that vasculature, it's the blood vessels, it's going to make it easier for the heart to pump blood around through a larger straw than a smaller straw. So that's what it does. It makes the heart beat more efficiently, and each stroke has more contractive effect to push the blood around, and then we're pushing it through a larger space, and that just makes the work on the heart much easier. The reason why we like to use this drug for specific things that it works for congestive heart failure, usually due to mitral valve disease or dilated cardiomyopathy, is that it's thought to increase long-term survivability in patients. So if we're also increasing the length of life of an animal, that's a real win-win situation. And that doesn't occur with many of these other drugs. So how does this drug work with mitral valve insufficiency? That should sound really familiar. You guys have a case study, so we're going to talk a little bit about how the drugs work with that situation. I'm going to show you this player. I'm going to be as brief as I can about it, and you can explore this on your own. But it's going to show you what a normal mitral valve should look like, so how it works. So here's a normal mitral valve. It's closing. The blood is going from the left atria to the left ventricle, closes, and the blood goes in one direction. So with regurgitation or insufficiency, and this also is a prolapse, this valve is going up into the atria. But you can see this little splash of blood. Some is going back up into that atria, and eventually that will cause that atria to remodel and become larger because it's just having to hold more blood. Not all the blood is going in one direction. Some is coming back up. All right, so as I said, you can explore that a little bit more on your own. So how this helps, we're not going to actually change the valve with the pemobendin. What we're going to do is we're going to make the heart more efficient and stronger at pumping blood out of the left ventricle, and we're going to make the vasculature more a bigger straw and easier to push the blood out. So really the whole idea is we're going to force more blood into the aorta, which is where we want it to go, rather than back up into the left atria. Does nothing for the valve, it just simply makes it easier to pump it out the aorta.